Morning. Today we are going to finish. I'm going to get on the right frame first. There we go. Today we're going to finish our content in Chapter 12, and we're going to go through a little bit of the primer on orbital mechanics, and we're just going to spend today on that primer. So if you come over here to the to our Moodle page and you look at the homework for Chapter 12, you'll notice that the problems 12, 14 up through 67 are found up to page 760. So I am going to put a couple more problems up for section 12.2, and all I really want to do on that, I want to turn on my edit. I'll go ahead and just do it right now while we're talking. I'm just going to put up a couple problems that will address angular momentum, and I'm not going to address it as angular momentum being conserved under a central force. I'm going to address it as angular momentum in general, and I'd like to do a couple of different problems with different coordinate systems. So if we take a look at the homework, I'm just going to give you two problems here. So problem set 3, which is from section 12.2, we are going to do problem 12.76, which is a really interesting problem, and you really need to use polar coordinates for that, or radial transverse coordinates. If you try it with any other set of coordinates, it kind of looks like you might be able to do it with normal, tangential, and you'll make yourself nuts. So just go with the polars on that one. And then we might do just one other one, I think 1278, which will just be a universal gravitational problem. I think you'll find that one relatively quick. So those will be the two problems, and that will be the end of the material for Chapter 12. And today we're going to spend some time on the primer for orbital mechanics. Now, the one thing I do want to let you know is that there will be a quiz posted here. The way that I do quizzes is, I haven't added any questions yet, so it's really easy. But tomorrow morning, I will add some questions to the quiz. And what I want you to do is, the quiz is timed. You'll have an hour to do it. And it's open book, open note, everything that you want. But there will be 5 places that you'll need to fill answers in. And then within that 1 hour time limit, I want you to do the 5 answers on the quiz and then email me your work, because the work that you do for the quiz is actually a significant part of the quiz. But I want you to email it to me within that hour time frame. Okay, so in other words, I'll have a timestamp from when you started your quiz, and then I'll have a timestamp from the email that you send me of your work. So don't change any work from the online quiz to the written quiz, okay? And what I'm really doing here, the quizzes, there'll be 2 quizzes only. They're worth 10% of your total course grade, so they're significant, but they're not going to, kill you. What I really want to do is have an opportunity to give you some close feedback before the first exam. Because when we do the exam, the midterm exam, it'll be worth 40% of your grade, and it will be 4 problems in a timed format. So you'll have 2 hours or 2.5 hours to do 4 problems. And so, and it's worth a lot of your grade. So we need to make sure that you know what I'm looking for, so that I can give you some serious feedback and make sure that that you don't have any misconceptions going in. So that's the main purpose.
Before Christmas break then?
The midterm is in October.
Christmas break, that'd be
the final. That's correct. See, good job. But we have 2. We have our midterm is going to be no later than Friday, October 11th. So we're marching toward that, and there'll be 4 chapters, and the material does not get any harder. Actually, I think I hesitate to say the material gets easier, but I will definitely tell you it doesn't get any harder. You know, we sort of hit the ground running in this class. So if you're coping with the material right now, you'll be just fine. So do the first 4 chapters, have a midterm exam, then we do the last 4 chapters and have the final exam. But in between, we have a homework set every chapter and a quiz midway between the beginning and the midterm and between the midterm and the final. So that's kind of the story. So at this point, do you guys have any questions about chapter 12 or about angular momentum or anything at all that you would like to discuss? Okay. Well, one thing that I wanted to do then is going over here to the primer. If you had opened this before, I split it a little bit differently. In other words, this is the material, the written material, the text, and I've split it so that all of the lessons are in this. So we have, and you're not going to have to do all of them, but they're, as AJ pointed out, the math in these is pretty easy. Not easy, but it's not as complicated as the stuff you've been doing so far. And one of the reasons that I like this primer and that I use it in this class is exactly because of that. Because I feel like you get, if you think about math as being our biggest tool as engineers, most of us are very comfortable with math and we like using math. When you get something like this primer that really focuses on the concepts and doesn't use a lot of math, you get a lot of conceptual, you get a lot of bang for your buck, so to speak. You know, so it's not the whole picture. We can't approach engineering as, let's minimize the math. But when we have an opportunity to get into the concepts without doing a lot of math, I just think it's a nice way to view not mathematics and pure science, but an applied science and engineering. So I wanted to present that to you. I also wanted to have this primer available to you so that you can print it off or download it, and in the future you may use it when you get into some significant rotational stuff that's going to require a lot of math. So I wanted to have that available to you. So anyway, to give credit where credit is due, this primer was written by Robert and Mary Williams, who were a married couple who were also rocket scientists with the Jet Propulsion Laboratory. And I was fortunate enough that they offered this to me to teach my classes from. And they had written it for a very, the child of some friends of theirs who was very interested in orbital mechanics. But he was a little bit younger, so his math level wasn't so great. So the Williamses took it upon themselves to, as rocket scientists, to think, how can we talk about orbital mechanics without a lot of math? And so it's unique in its approach. So it starts with the idea of Kepler's law and Newton's law of gravitation. And really, Kepler's law is probably the biggest deal when it comes to orbital mechanics and to understanding orbital mechanics. And then Newton's law of gravitation is also they're both very insightful, and they give a lot of physical meaning to a particular kind of situation. But the one thing that I've stressed over and over again, and until you work the problems, this may not be as apparent as to why I've said it like 27 times, but it's very important to note that this only applies to the piece of angular momentum where you're acting under a central force, because that's the only case where angular momentum is conserved. Because angular momentum, first of all, has to be taken about a point. So if you take angular momentum about at 2 different points, the angular momentum is different. But when you have a central force, in other words, you have a planet in the middle, something orbiting it, or sun in the middle, something orbiting it, you have a situation where all the force is directed toward the center of the body that is being orbited. And so Kepler's law can be simplified in this humongous area of applications. So we talk about satellites in circular orbits, transfer orbits. I had a little conversation with AJ. There was a movie that came out a few years ago called Hidden Figures, and they talked a little bit about transfer orbits, and it's actually historically factual, where a NASA scientist named Katherine Johnson actually with the help of our colleagues, a little bit inaccuracy in the movie, it was a little simpler, but they developed this way to transfer orbits from one altitude above the Earth to another. And it's very important because the energy of the satellite as it transfers can either make it spin into the Earth or spin out into outer space, and you don't want those things. You want it to go from one orbit to another orbit, and doing that requires some pretty it is complicated math. It's pretty complicated math, so we're not going to do it in here. But they talk about different ways of doing that transfer orbit. Then we're not going to be covering it in here, but they talk about rocket requirements and characteristics, which is also very interesting. They have some jet fuel calculation problems and what the ratios of different things look like. So if you have an interest in that, this is pretty cool. And then we talk about other orbits. Most naturally occurring orbits, when I say most, I really probably mean all, but I'm going to say most just to hedge my bet, are elliptical in nature. And the object that is being orbited is at one of the foci of the ellipse. So the speed of the orbit changes in a relationship based upon its distance from that focus. So they talk a little bit about that. Now, circular orbits mathematically are a lot simpler to deal with, and satellites above Earth tend to be in circular orbits, circular is okay to say. But the elliptical orbit has more applications for naturally occurring orbits. But then you have periods of speeding up and slowing down, whereas a circular orbit is generally speaking sustained at a constant velocity. And that constant velocity is because the force is constant. What's the force of a circle? If you have a force in the center, it's v squared over m times v squared over r. So those things are not independent. Those are all related to each other. The velocity of a circular orbit, how high above the orbited body the orbiting body is, and of course the mass of the satellite. So anyway, then we have 7 lessons, which I have put in the second part. So all 7 of the lessons are here. And no, I'm not going to make you do all 7 of them. These are for your future concern as well. I'll put a few problems on that we'll just talk about so that we can kind of get a handle on sort of the way this works, because it feels a lot different than your textbook. But in the future, I think this may be something that you would like to work with. So anyway, the basic physics for orbital mechanics has been around since the 1600s, and Johann Kepler and Isaac Newton are sort of the big names that come up. And I understand that Isaac Newton, if you ever have a chance to read a biography of Isaac Newton, he was an odd fella. Awfully smart, awfully insightful, but not your typical person. So they said, one of his biographers said that sometimes when he would wake up in the morning, and he was single his entire life, he made a decision to stay single because he didn't think he could cope with the emotional pressure of not being single. So he had a housekeeper, and his housekeeper said that sometimes when she would wake him up in the morning, he would swing his legs over the side of the bed and just be like so struck by the thoughts that were going through his mind that he would sit immobile and uncommunicative for hours, just thinking about everything that hit him when he first woke up. So that's not how I wake up. My first thought is coffee. Where's my coffee? But he was thinking bigger thoughts than me, obviously. He was thinking about the nature of the universe, or I'm just thinking about my first cup. But anyway, Johann Kepler was the first scientist to figure out the rules, and basically, in words, there are Kepler's Law, that planets orbit the sun in ellipses with the sun at one focus. I'll just draw that for you a little bit. A line from the sun to the planet sweeps out equal areas and equal times, which is really cool. And the period, which is the time it takes to go around once, of a planet's orbit is proportional to its distance from the sun. So what does that mean? It means Mercury goes around the sun faster than does Venus, than does Earth, and so on, until little Pluto, which we don't even know if it's a planet anymore. It's kind of got demoted a few years ago, maybe, we don't know. But anyway, so Pluto takes, I don't even remember, 248 years or something like that to go around the sun. So, and I think Mercury, the closest one in, takes 88 days. So big difference. And the other part is that you may already be aware of this, but the distances in space are just so vast. We can't even really comprehend them. I remember in grade school, they talked about if you put the sun as being a pea in the middle of a football field, so bringing this down to like what we knew at that point, that like would be Mercury, Earth, Mars, and then clear out here at the edge of the football field, Pluto would be like a pinhead. Not even a pinhead. I think maybe you had to make this a basketball, and then this would be a pinhead. But that's sort of the scope. Or maybe it was even farther than the football field. I can't remember. It's just huge. The amounts of space are just huge. But when we say that here's our sun, right? Doesn't really look like that. But there you go. If you were to look at a planetary orbit, there's two foci in an ellipse, and once again, my drawing skills have eluded me because they should be farther down. In other words, there's an axis. They call this the semi-major axis, and this the semi-minor axis, and the foci are right here and right here, equidistant from the edges. And so the sun would be at one of the foci, and the speed here is going to be different than the speed here because it's proportional to the distance from the planet. And it says a line from the sun to a planet sweeps out equal areas in equal time. What that means is that if you say, and this would be that if we have an orbiting body in an elliptical orbit, that if this chunk of time represents 1 hour and has one aerial unit, 1 unit of area, whatever that is, if I go from here to here and I make something that has an equal area, like this, that this would represent the same amount of time as this, if this area were equal to this. So as you get farther and farther out, the sliver is going to get skinnier and skinnier, isn't it? So it's interesting to think about this as well, because what that means is that it's going to take as much time for it to go from here to here as it is from here to here, because that's the path of the planet. But you can work that problem geometrically by a swept area. And there's actually an instrument now in AutoCAD. You may be able to see how to make that area calculation very quickly. There's actually a mechanical device called a planimeter that would do this for you, so that you could do this. And planimeter, I have one. I actually have a working planimeter, so I'll bring it in next time and show it to you. But you can sweep areas like that and determine, like I use it a lot for cut and fill calculations on roadways. Nothing quite this glamorous, but same sort of thing. You can find, like, if you got so much dirt over here and you want to move it over here, do you have enough dirt to move from here to here? So that's always, it's not the most glamorous aspect of engineering, but it's still, when you're building road beds, it's still pretty important. All right, so the last one is that the period of a planet's orbit is proportional to its distance from sun, which is, as we talked about, Mercury goes around the sun faster than does Pluto and so forth. So in general, naturally occurring orbits are elliptical. And if you notice an elliptical orbit, as the semi-major axis collapses, it becomes more and more circular. So in one sense, mathematically, a circle is just the same thing as an ellipse with the same dimension for a major and minor axes. All right, so one thing that we become, oh, you want to see this probably. Let's come over here. Let's get the document cam. Let's get the podium PC. There you go. It's a better drawing. So when we take a look at this drawing, we talk about that idea of swept areas. And so this entire diagram really describes Kepler's law of planetary motion right there. So we talk about these elliptical orbits. And if you notice, as we move, if we were going from one elliptical orbit to another elliptical orbit, that's where we would have to talk about a transfer orbit. And because everything changes about the energy of a satellite in transfer, you boost it. If you want to get it into a higher orbit, you have to fire a little rocket to get it moving from one to the other, and you lose mass and you gain energy. You take mass and you combust it. You don't lose mass. I mean, mass, it goes into combusted stuff, but it's no longer on your rocket. So you combust some mass of fuel and you increase the energy level. But if you don't do that enough, it will tend to spin out, get caught into the gravitational, the gravity of the thing that's orbiting. And if it's too much, it'll spin out and not go into orbit at all. So the balance of getting the transfer orbit blast, and there's a better word for that. It's not coming to me right now. But to get that energy calculation for the transfer orbit is a big deal. And it turns out that it is a shape. I believe it's a part of a parabola that you have to transfer from one to the other, but I'm not 100% sure. Okay, Newton's law of gravitation. We talked about Newton. And so once again, this is all pretty old stuff. He came up with the universal laws of gravitation. And in a biography of Newton, I read that this was one of the things, somebody asked him about a question about Kepler's law, and he answered it sort of intuitively. And the person said to him, "Why is that?" And it struck him that he didn't really know mathematically why, so he told the visitor, "You will have to go now." And he basically locked himself in his office for 2 years and did the math. So, like I said, he was a little bit more obsessive than most of us, but odd guy, but we got a lot of science out of that. So anyway, so when we talk about, this is cannonball, which is basically that trajectory idea. But Newton's law of gravitation just tells us that the energy is directed inward, angular momentum is conserved, and that it's basically, if you have a circular orbit, you're really talking about an F-T coordinate system. And so you can attribute all the velocity to, or all the dv/dt, all the acceleration to what's going on in the path, and all the change in direction to the center of the circle. At the bottom, I have written 1 nautical mile equals 6,076 feet. I just think that's an important thing to know, especially since most of us here are from landlocked areas where nautical miles don't come into play very often. But the Navy and the Air Force, a lot of the Air Force stuff came out of the Navy. So aerial navigation, even if you were flying a little Cessna plane, is reported in nautical miles and knots, which a knot, K-N-O-T, is an abbreviation for nautical mile per hour. So a nautical mile is a little bit longer than a regular mile, which the name of is called a statute mile. Statute mile is 5,280 feet. So just more fun with U.S. units. So you go. So this is just a breakdown. We actually looked at this in chapter 12, but basically we have Newton's law of gravitation. They rewrite it a little bit, and then they come up with this constant mu. And if you look at the equation, mu is actually G times capital M. So mu is specific to a particular planet. It's just or something that's being orbited. So it's just the mass of the orbited body times Newton's law of gravitation, or times Newton's universal gravitation constant. So if we take a look at that, we also know that force, when we talked about that normal tangential stuff, the force directed toward the center is equal to mv squared over r. So for a body in orbit, in a stable orbit around another body, we can equate those two. In other words, that's what has to balance. That force of gravity as defined by the normal force equals mass times acceleration, where acceleration is that v squared over r term, has to be equal to the gravitational attraction of the planet. Otherwise, if the gravitational attraction of the planet is too great, the object will spin into the planet. If it's not great enough, it will spin off. So to maintain a stable orbit, those two things have to be equal to each other. And so basically we come up with mu over r is equal to v squared. What that really tells us, because mu is specific to a planet. So if you're orbiting the Earth, you have a particular mu. If you're orbiting the Sun, you have another particular mu. But basically, that the velocity of the orbit and the distance of the orbit from the center of the orbited body are not independent of each other to maintain stable orbits. That means if a satellite is at a particular elevation, it's also at a particular velocity. So that's kind of an interesting consequence of that stability. Otherwise, you have to boost it. I mean, if it starts to slow down, you can either let the orbit degrade or you can boost it. But in order to keep it in orbit, that's what has to happen. Okay, this equation talks about the period, and this is specific to a circular orbit. You can work the calculations for an elliptical orbit as well. But basically, P is period, or in other words, how long it takes to go around one time. So you may have heard the term geosynchronous orbit. That means, like, if we have satellites and we want them always to remain in the same spot in the sky above us, that means that it's rotating at the same speed as the Earth and in the same direction as the Earth. So a geosynchronous orbit has a particular velocity, which is our velocity, and it also has a particular distance. So geosynchronous orbits are all at the same elevation above the surface of the Earth, if they're circular. Which they almost, well, I won't get into that, but we'll just leave it at that. So if a circular orbit that is geosynchronous always has the same elevation, the same altitude above the Earth. All right, and so this just goes through a little bit on math, and we find that this just reduces to the period. We know what this is, and I think that's about it for that page. All right, so then just a little bit, we talk about low Earth orbits and the radius that we consider. This circle, the inside circle, represents the Earth, so R sub E is the radius of the Earth, and H is the orbital distance, or the height above the surface of the Earth. And so it gives you a few more statistics here in nautical miles about what a radius would be, in terms of if you have something that's 220 nautical miles above the surface of the Earth, what you would use for the radius. In other words, in the calculations, you're talking about from the center of the Earth to the altitude. So it's the entire thing. Okay, so we talk about, then they talked about the space station, which is still around, but what the period of the space station is. And the International Space Station had a period of about 92 minutes and 34 seconds. And then the velocity is this many feet per second, which you can report in nautical miles per second, or knots, which would be nautical miles per hour, or statute miles per hour or second. Okay. Then the last piece I want to talk to you about today is the idea of a geosynchronous orbit, which just basically is what is the height above the surface of the Earth, and what's the velocity of a satellite that always appears to be in the same place in the sky. So this is really interesting because, and it just talks about what the period, of course, is going to be 24 hours. So if you do that, this is what you find. If you run through the numbers, the geosynchronous radius, and if you look at that, that is not the height above the Earth. That is the distance from the center of the Earth. 22,765 nautical miles will establish a stable geosynchronous orbit. So that means that the height is 19,325 nautical miles above the Earth. So that's kind of an interesting fact as well. And I think I had mentioned last time, but we have quite an array of satellites. I wonder what we look like from outer space. I think we look like we got a bunch of junk up in the sky, and it's pretty patterned, but I don't suppose it really looks pretty patterned. I bet it looks pretty random. But there are systems of satellites that work together as well, and I think I'd mentioned earlier that there are different systems that we use for GPS, and there's some from the European Space Agency, there's some from Russia, some from the United States, and so forth. And sometimes they talk to each other, sometimes they don't. It just kind of depends on who's getting along with who at the time. But back when they started doing GPS, I think, Logan, you may remember from surveying that when GPS first became a thing, United States, he wasn't doing surveying at this time, but I mean, we talked about it, is what I'm saying. But the United States government had what they called selective availability, where they would turn off signals from certain satellites at certain times. And all of the original GPS satellites were military in nature to begin with, so they wanted to make sure that somebody wasn't going to be able to back triangulate and shoot down a satellite. So they were very careful, so they would just sort of randomly turn off the signals from the satellites sometimes. So there were times where you could not get a good signal fix. And there were times in the beginning of GPS satellites, in GPS surveying, where you'd actually have to wait. Like you'd get an ephemeris and you would determine when there were going to be good satellites in your part of the world, and then, you know, if it was 2 a.m. or whatever, that's when you would go surveying, because that's when the satellites were up. Because of course, if they're below the horizon, you're not going to get any information. The other thing is, if you think about it, if they're in a straight line, you're not going to get good information because you don't have that spread. So you just get like a very one-dimensional picture, and especially elevation gets shot when you do satellites in a line. That has not been a problem for over 10 years because there's so many satellites now. But the other thing I just thought was interesting is, and I've got a bunch of videos up on my YouTube channel about this, but basically GPS satellite system is the only system where they reduce, you think that it's going to be sending a signal back in time, but it doesn't, because we don't have any clocks that are precise enough to measure distance equals rate times time. We can't, the rate, which is electromagnetic energy, the speed of light, is just too fast. So the clock would have to be too accurate. We don't build clocks like that. So it does a 4-dimensional space-time calculation, and turns out that we have to do a relativity correction for that. So as far as I know, it's the only established global scale technology that requires corrections for Einstein's law of relativity. So anyway, general relativity. All right, so there's some interesting pieces of the puzzle. And this talks about transfer orbits. I'm not going to go into it. But if you want some light reading, it's extraordinarily interesting. So take a look if you have a chance. Now, having said that, I'm going to, like I said, I do not think that you're going to, I think you'll be pleased with the level of math. But we've only done sections 1, 2, and 3. So that's all that we're going to do in terms of lessons. If you want to take a look at 4, 5, 6, 7, and so forth, please do. But if you would, let's do the odd number problems for lessons 1, 2, and 3. So do 1, 3 here, 1, 3, 5 here, and 1, 3, 5 here. Okay, and I'll write that up. That's going to be your last homework assignment for Chapter 12 and Orbital Mechanics. So Friday, you have a homework assignment due, and you have a quiz that will be posted. So you can do the quiz over the weekend if you would prefer. I mean, I'll keep it open over the weekend. But if you have any questions, let me know. On Friday, I will not cover any new material. We will not start Chapter 13. So I may or may not have a lecture. But what I will do is I will be here, and if anybody comes in with questions, or if anybody in computer land has questions, if you send them to me, I'll spend Friday answering questions and doing problem solving. Okay? But so look for a lecture for Friday, but even odds whether we're going to actually have a lecture for that day or not. So, all right, do you guys have any questions for me? All right, well, you get to get out early, 10 minutes early today. So, yay! All right, so please let me know if you have any problems or questions. And I will be here all day tomorrow, so don't hesitate to come by if you need me. I actually have to leave a little early this afternoon to go do a thing with my mom in Billings. So, but I will be here all day tomorrow if you need me. So, all right. Well, you guys have a great day, and we will see you soon. Thursday, Friday, someday.